Okay, welcome back everybody. So, in last lecture, I had told you all how to find eigenvalues for a given matrix. So just a reminder, um, eigenvalues for a matrix A that is an n by n matrix are roots of the characteristic polynomial of A. Okay, remember the characteristic polynomial of A is the determinant of A. You could think of it as the determinant of A minus Zi if you like, or determinant of, well, I won't rewrite this as a different thing. You can define it as this, or I think the textbook actually switches the order of these. For the 2 by 2 case, it's not going to matter, but in fact, as far as finding the roots of these things, it's not going to matter either, because it's just going to change this by plus or minus 1. So so that is not going to be an issue regardless. So we could just as well as define this as going in the other direction. And so whether you wanted to write it as this or this, it doesn't really matter. I believe the notes writes it like this. Like I said, this doesn't matter too much. So the main thing to remember is for the 2 by 2 case, we actually had a shortcut here, right? So if A is 2 by 2, then the characteristic polynomial we could write as z squared minus trace of A times z plus determinant of A. This is a handy shortcut, allowed us to find the characteristic polynomial really quickly without having to go through the whole algebra of computing that determinant, right? Now we did compute the determinant, and we do this the long way for one example, but in general you can use this this shortcut and be happy with that. So a couple of facts directly from this. So since eigenvalues for a matrix A are roots of some polynomial, okay, notice a few facts, right? So one, in the case that A is a 2 by 2, this polynomial is a quadratic, right? So it's a degree 2 polynomial. But in general, what is the degree of this characteristic polynomial? So if A is an n by n matrix, then the degree of the characteristic polynomial of A is n. Okay, you can check that yourself if you really want to. Here's an example, right? I'll do this, but I'm not going to even do it fully. I'm just going to write, okay, well, if, let's say A is the 3 by 3 matrix. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Then Zi minus A, what does that look like? This would be the matrix, so Z times I is just the matrix that has Z on the diagonal. So this would be Z minus 1, minus 2, minus 3, minus 4, Z minus 5, minus 6, minus 7, minus 8, Z minus 9. Okay. Computing the determinant of this, how does the determinant of this work? So determinant of zi minus a. This would take me a little bit of effort, but whatever this thing is, okay, what am I going to be doing with these terms? I'm going to be multiplying, right, at worst, z times z times z. That's the most I can get out of this. If I follow this determinant through, that's exactly the sort of thing I'm going to get. I'm going to get a degree 3 thing here, right? I'm going to get a cubic, okay. Now, it might be a little bit harder to see that I'm going to get a cubic here because this is a matrix that has no zeros here, so I'm actually going to have to do this determinant fully. I'm not going to do that, like I said, because we're not going to worry about 3 by 3s and higher. There's a couple of examples in the notes that show this, but we're not going to do that. Typically, this is skipped in 246. But the way that this works is, it would be this thing times the determinant of this sub thing. Well, let's just go ahead and here. I'll write it out just to do it, just for completion's sake. So here's zi minus a. The determinant of zi minus a would be z minus 1, okay, times the determinant of this smaller matrix, z minus 5 minus 6 minus 8, z minus 9, minus, because that's how determinant works, it's an alternating sum thing, minus 2. So I'm just going across the top row because no row or column is any better, really. So this would be minus 2 times the determinant of the submatrix where I've deleted the top row and middle column instead of, in this one, I had deleted the top row and first column to get this as my submatrix. Here I've deleted the top row, middle column. For the last term, I will delete the top row and third column. So this would be determinant of minus 4, minus 6, minus 7, and z minus 9. Okay, plus minus 3 times the determinant. Again, submatrix here, I've deleted top row and last column. So this is minus 4, z minus 5, minus 7, minus 8. Okay, so the point, I'm not going to go through all this, I'm just going to do the first term. So the first term would be z minus 1 times this determinant would be z minus 5, z minus 9, minus 6 times minus 8, because we know how to compute determinants of 2 by 2s, plus some other stuff. The point is that in this term, I'm just going to have a z minus 9 times some constants and then some other constants. Here I'm going to have a z minus 5 times some constants and other constants. So those are only going to contribute degree 1 terms. This is going to contribute a degree 3 term because I'm going to have z minus 1 times z minus 5 times z minus 9, and then some other stuff, right? So the whole point is that the degree of, the degree of the determinant of zi minus a is 3 in this case, is the point, because of this term, okay? All right, that's just showing you how this works. Now, in general, as I said, this is actually a degree n thing. So first fact, degree of the characteristic polynomial of an n by n matrix is n. Okay. All right, but that tells us some stuff, right? This tells us by this thing that we talked about when we first talked about finding roots of the characteristic polynomial, not of a matrix, but of the, but in the case where we're dealing with higher order linear single equations, right? Not systems of equations. When we're talking about the characteristic polynomial in that context, we mentioned that, oh, the degree of the characteristic polynomial tells you that counting with multiplicity, you know exactly how many roots you have. Okay, and that's just the degree, that's n. Okay, so another way of saying this then is by the fundamental theorem of algebra, this means that for a n by n, characteristic polynomial of A has exactly n roots, counting with multiplicity, as usual. I.e., A n by n has exactly n eigenvalues, again, counting with multiplicity. So, it is possible for a matrix to have repeated eigenvalues, and this happens exactly when those eigenvalues show up as repeated roots of its characteristic polynomial. Okay, so let's do an example. Okay, so find all eigenvalues of the matrix, we'll call the matrix B, and this is the matrix 4, minus 1, 1, 2. Okay. So its characteristic polynomial is p sub b of z, which, as I said, since this is a 2 by 2, this is z squared minus the trace of b times z plus the determinant of b. Well, what is the trace of b? Trace of b is 4 plus 2, which is 6. And the determinant of b is 4 times 2 minus 1 times minus 1. Okay, so this is 8 minus minus 1, so that's plus 1, so this is 9. And so this becomes z squared minus 6z plus 9, which of course factors z minus 3 squared. So roots of the characteristic polynomial are z equals 3 and 3, i.e. lambda equals 3, 3 are the eigenvalues of B. So the only roots of that characteristic polynomial is 3 is a double root. Okay. Thus, the eigenvalues, counting with multiplicity for this thing, this is 2 eigenvalues, but it's really a single eigenvalue that's a double root of the characteristic polynomial. So this is an eigenvalue of multiplicity 2. Okay. So that is how that works. Okay, so the only eigenvalue really is 3, but it occurs as a double root. Okay, so it counts as 2. All right. Let's do another example. So as I've mentioned before, this entire time we've kept eigenvalues open as numbers, right? I never called them scalars or constants. And that's just because I didn't want to bias you towards thinking about them as real numbers. You know, since they arise as roots of polynomials, that complex numbers are going to show up, right? There's no way of getting around it unless you specifically like say that's not, I don't want to consider things like that. But the problem is you see the ease with which complex numbers show up here. So there's really no reasonable way of not talking about them. So let's find all eigenvalues of the matrix C, which is the matrix 3, 2, minus 2, 3. Okay. So, first step, its characteristic polynomial is p sub c of z, which is, again, because this is a 2 by 2, z squared minus the trace of c times z plus the determinant of c. Well, the trace of c is again 6, right? It's 3 plus 3. Okay. The determinant of c is 3 times 3 minus 2 times 2. So this is 9 plus 4. So this is 13. Okay. So then the characteristic polynomial is z squared minus 6z plus 13. Well, we could use the quadratic formula here, but I could also just notice that this is z squared minus 6 plus 9 plus 4, right? So this is z minus 3 squared plus 2 squared. So solving for roots here, the roots are z equals 3 plus or minus 2i. Thus, the eigenvalues of c are lambda equals 3 plus or minus 2i. So it has two distinct eigenvalues, 3 plus 2i and 3 minus 2i. Okay. So it has those two distinct eigenvalues, but they're both complex numbers, right? So when we return to this, right, this case is going to be just slightly, like 10% trickier than the case that doesn't involve complex eigenvalues. But really, you're going to see that it's not going to be too much different. It's really, if you understand basic algebra, complex numbers, which you've already had to use earlier when finding, say, the real and imaginary parts of particular solutions, right? To find particular solutions, you had to understand at least enough about complex algebra to find real and imaginary parts of things that involved, e to the complex number times t. Right, so that alone is already enough to understand what's going on here. So we'll see examples of that here in just a second. But anyway, this is just a nice, simple example showing, like, look at C, right? C is, not only is it a matrix that only contains real numbers, it's actually a matrix that only contains integers, right? So it's pretty much as nice as possible, and it has complex eigenvalues. Okay, so complex eigenvalues are not to be thought of as like some degenerate case here. They're completely normal case, and we can deal with them in the exact same way, really, that we can deal with these others. It only takes a little bit more, a little bit of a tweak to understand what's going on here, but that's it. Okay. And so, now what do I want to do? So finding eigenvalues is as simple as finding roots of polynomials, right? Once you understand how to write down the characteristic polynomial, finding eigenvalues is just finding roots of that polynomial. So you are very well equipped to deal with that. So now the big question, and it's the last remaining thing to do before I can actually say how to use this new data that we have. All right, so the big question is, all right, how do I find eigenvectors associated to some eigenvalue? Okay, so eigenvalues are roots of polynomials. So once I understand writing down characteristic polynomial, finding its roots. That's it. Finding those is easy. But how do I find eigenvectors corresponding to those? Okay. Well, to see that, right, let's recall that if lambda is an eigenvalue of A, then an eigenvector, we'll call it V, associated to lambda satisfies A V is equal to lambda V. Okay. Now, there are two ways to go about this. Okay. One is the Math 240 or 461 way. Really, this is the normal way of going about it, which is simply solving this. What I mean by solving is we write out the equation AV is equal to lambda V, and then we just find the general solution to that matrix equation. Okay. Now, if you're doing this in the Math 240 or 461 way, technically this is a process that's learned in 240 or 461 where you write out what's called a basis for the null space of this matrix A minus lambda I. Okay. So you're finding a basis for that null space, if you like. Another way of writing this, so solving this is the same thing as, i.e. solving A minus lambda I, V is equal to 0. So it's solving this homogeneous matrix equation. Okay. All right. I'm going to go through how to do it this way. The second method is to use what's called the Cayley-Hamilton theorem. This we're going to do for 2 by 2's. 2 by 2's only. This first method works for anything. So this works for n by n's. Okay. Using Cayley-Hamilton is going to work for 2 by 2's only. Okay. Now, how does this work, and how does this factor into basically any of the stuff that I care about here? So first of all, what does the Cayley-Hamilton theorem say? So Cayley-Hamilton says the following. Remember how yesterday so in last lecture I wrote this this way of plugging in a matrix into a polynomial. So recall how to plug in a matrix to a polynomial. Okay. All right. So what does Cayley-Hamilton say? It says that if you plug a matrix into its own characteristic polynomial, you get 0. You get the 0 vector. Okay. Now, how does this help me at all? Well, the way that I think about this is, now for a 2 by 2 matrix A, P sub A of Z can be factored always as Z minus lambda 1 times Z minus lambda 2. Okay. And so P sub A of A, by Cayley-Hamilton, this is equal to the 0 vector. By how to plug this in to this becomes A minus lambda 1 times I times A minus lambda 2 times I. Okay. But so what this means, compare this with, or maybe I'll just write it here, recall from part 1 on the previous page, here, the math 240, 461 way, we want to solve this equation, right? But from 1, since A minus lambda 1 I, whatever that is, times A minus lambda 2 I is equal to the 0 vector, then any non-zero column of A minus lambda 2 I, okay, solves the equation A minus lambda 1 I times V is equal to 0. And similarly, any non-zero column of A minus lambda 1 I solves the equation A minus lambda 2 I times V is equal to 0. What this means is rewriting this very slightly. Thus, Cayley-Hamilton says, and this is very important, any non-zero column of A minus lambda 2 I is an eigenvector for lambda sub 1, and any non-zero column of A minus lambda 1 I is an eigenvector for lambda sub 2. Okay. Now, the benefit of using this is that this is a slightly shorter, more direct way of doing this for 2 by 2s. The downside to using this is that if I only showed you this, then technically you would be completely unable to find eigenvectors for 3 by 3s or higher. Okay, so it's not good that you only see this, but if all you're interested in is doing this for 2 by 2s, and in this course, for all these problems we're going to do, all the matrices in question are going to be 2 by 2s. So for us, this is very relevant. Then Cayley-Hamilton's a pretty nice way of doing this. Now, it turns out that 2 by 2s are already simple enough that doing it in the normal method is actually not substantially longer. But still, this is a more direct thing. So an eigenvector for lambda 1 is found from non-zero columns of a minus lambda 2I, and an eigenvector for lambda 2 is found from non-zero columns of a minus lambda 1I. Okay. Okay, and so let's do an example of these things. So first, let's use our favorite matrix that we've used so many times in these problems, 3, 2, 2, 3. So recall, if you like, this has eigenvalues. What? So eigenvalues of this thing are what? Well, we did it before, but let's just quickly do it again. Can't hurt. So characteristic polynomial, right, is z squared minus the trace of a times z plus determinant of a. So trace of a is 6, determinant is 9 minus 4, so it's 5. So this is z squared minus 6z plus 5. We've already seen previously this definitely factors as z minus 1, z minus 5. So this has roots 1 and 5, so it has eigenvalues, lambda equals 1 and 5. Okay. All right. And so I'm going to treat 5 as the first eigenvalue. So let's, I want to find eigenvectors. I want to find eigenvectors for lambda 1 equals 5. Okay. Let's go back to the two methods. I have two ways of doing this. Either the Math 240 or 461 way, which means just solving this resulting equation, or the Cayley-Hamilton way. So let's do this by the 240 method, right? So I'll use the normal method of doing this. Okay, so that is, I look at the equation a v is equal to 5 times v, right? This is the equation that arises for this first eigenvalue, lambda 1, right? So really this is the equation AV is equal to lambda 1 v. But lambda 1 is 5, so this is AV is equal to 5v. Okay. Okay. Well, what is this? Well, if v is a vector that has components, we'll call them v1 and v2. Okay. Then the resulting homogeneous equation, right, would be like AV minus 5v is equal to the 0 vector, or as we were writing before, a minus 5I times v is equal to 0. Well, what is a minus 5I? Well, the matrix A is 3, 2, 2, 3. So this is the matrix 3, 2, 2, 3. Minus 5 times the identity matrix 1, 0, 0, 1. So what is this matrix? This is 3 minus 5, so that's minus 2. 2 minus 0, so that's just 2. 2 minus 0, so that's 2. 3 minus 5, so that's also minus 2. So a minus 5i is minus 2, 2, 2, minus 2. Okay. So then a minus 5iv is equal to 0 is really the matrix minus 2, 2, 2, minus 2 times the vector v1, v2 is equal to the 0 vector. That is what this equation is. Okay. So rewriting this as a system, this would be the system minus 2v1 plus 2v2 is equal to 0, and 2v1 minus 2v2 is equal to 0. And I want to solve this system. Now notice how this works, right? It turns out that both of these equations are actually the same equation. I've just multiplied, say, this one by minus 1. Right, so if I multiply this by minus 1, I get minus 2v1 plus 2v2 is equal to 0. It's the same equation. Okay, so either of these equations I pick will work to solve this. We have some freedom here, right? We're going to have a choice, okay, because we're going to have a free variable. All right. Now, what we can do here is, say, just pick the first one. And if we pick the first one, say this one, this means that minus 2v1 plus 2v2 is equal to 0. So that 2v2 is equal to 2v1. So that v1 is equal to v2. So I have a choice for v2. Say that we choose v2 to be equal to 1. So choose v2 to be equal to 1. Well, since v1 is equal to v2, if v2 is equal to 1, this means that v1 is equal to 1. And so we have found a solution to this, i.e. the vector v, which is 1, 1. I'm going to label it as vector v1, which is the vector 1, 1, is a, so this is a solution to a minus 5i times v is equal to 0. Another way of saying that is that the vector v1, which is 1, 1, is an eigenvector associated to the eigenvalue lambda 1 is equal to 5. Another way of saying this is that 5, 1, 1 is an eigenpair for A, where in the first slot it's my eigenvalue and the second slot is my eigenvector. Now, one question you're probably going to have here is, does it matter that I chose this to be 1 instead of, say, 5? Right? So say at this point, instead of choosing this to be 1, I had chosen v2 to be 5. Well, then v1 is 5, and the vector that I would get instead is 5, 5. Is it wrong to say that 5, 5 is also an eigenvector associated to the eigenvalue lambda equals 5? No, it's not. Because remember, one of the things, when I first introduced eigenvalues and eigenvectors, one of the things that was true about them is that in general, you're going to have infinitely many eigenvectors associated to an eigenvalue. In fact, one really easy way of showing this or saying this is you could just take scalar multiples. So eigenvalues are typically not, or sorry, eigenvectors are not unique, right? They, in fact, the eigenvectors you find for 2 by 2s are typically only going to be defined up, or only going to be unique up to scalar multiplication. So take any eigenvector you want for an eigenvalue, scale it by a constant, so multiply by whatever constant you want to. So multiply by whatever constant you want to other than 0. Right, so don't scale by 0, that would be stupid. But any other scalar you want, scale by that thing, you get an eigenvector for that same eigenvalue. Okay, so scaling by constant doesn't change that. So 5, 5 is also an eigenvector for this thing. That's perfectly fine. Okay, 1, 1 we like better, right? The numbers are smaller, nicer, but there's actually, there's nothing wrong with, if I had written 5 and 5, 5 here, that's perfectly fine. Okay, so it's a perfectly valid statement. So this is an eigenpair for eigenvalue 5. Let's do the same thing for the eigenvalue 1. So for lambda 2 equals 1, the equation in question is a minus lambda 2I times v is equal to 0, which would be the equation a minus I times v is equal to 0. What is a minus I? Well, this is the matrix 3, 2, 2, 3 minus I, which is 1, 0, 0, 1, which is 3 minus 1, which is 2, 2 minus 0, which is 2, 2 minus 0, which is 2, and 3 minus 1, which is 2. Okay. So then this equation, a minus iv is equal to 0, is really the equation 2, 2, 2, 2 times v1, v2 is equal to 0, 0. Okay. So then writing this system, this is a system that contains, again, two equations that are exactly the same. Okay, in this case, they are literally the same equation. So let's take the first one here. What does this mean? So 2v1 plus 2v2 equals 0. This means that 2v1 is equal to minus 2v2, or that v1 is equal to minus v2. So if I choose v2 to be 1 here, again, then this implies that v1 is equal to minus 1. And so what that means is that the vector minus 1, 1 is an eigenvector associated to lambda 2 equals 1. Or, another way of saying this is that 1 minus 1, 1 is an eigenpair for A. Okay. All right. And so, just to recap, we had a matrix A that was the matrix 3, 2, 2, 3. It had eigenvalues lambda 1 equals 5, lambda 2 equals 1. And it had eigenvectors, or I'll write them as eigenpairs. So eigenpairs 5, 1, 1, and 1, minus 1, 1. Okay. Okay. So let's use Cayley-Hamilton instead. So for both of these, we use the usual way. So we used the usual way to find these. Let's use Cayley-Hamilton instead. So let's use Cayley-Hamilton instead. Okay, so I have eigenvalues, lambda 1 equals 5, lambda 2 equals 1. So an eigenvector for lambda 1 equals 5 is any non-zero column of a minus lambda 2I, which is a minus I. But a minus I, as we saw, is 2, 2, 2, 2. Okay, i.e. v1 equals 2, 2 is an eigenvector associated to lambda 1 equals 5. And an eigenvector for lambda 2 equals 1 is any non-zero column of a minus lambda 1I, which is a minus 5I, which, as we saw previously, a minus 5I is minus 2, 2, 2, minus 2. This is minus 2, 2, 2, minus 2. And so this means that I can pick the first column there. So v2 equals minus 2, 2 is an eigenvector associated to lambda 2 equals 1. So you saw how quick that was. Okay. You saw how quick it is to actually write this out. Now, let's just check that this actually gives us the same thing. I'm claiming from this first box that 5, 2, 2 is an eigenpair. Well, I already know that 5, 1, 1 is an eigenpair. Of course, I can multiply this eigenvector by 2 to get that 5, 2, 2 is also an eigenpair, so this is perfectly fine. Again, here, minus 2, 2, I'm claiming is an eigenvector for 1. Here, I already know that 1 minus 1, 1 is an eigenpair. So then if I multiply this just by 2, I get 1 minus 2, 2. That's exactly what I get here. So using Cayley-Hamilton would have been perfectly fine. Of course, you might say, oh, wait, well, say I'd used Cayley-Hamilton and I'd gotten these instead and I didn't see that I could actually make them simpler. Well, once you've used Cayley-Hamilton to get these vectors, you are welcome to scale them by whatever you want. Right? So there's always this act of, you can always multiply eigenvector by scalar and end up with an eigenvector perfectly fine. So there's no problem there. Okay, so this is how this works. Okay, this is how this works. Let's do 2 more examples. Okay, so let's revisit those earlier examples of finding eigenvalues and eigenvectors for specific. So I'm going to recall the following. So here's my next example. Find all eigenpairs of the matrix B, which is the matrix 4, minus 1, 1, 2. So we already saw from the previous example that this matrix has 3 as a repeated eigenvalue. So 3, 3 here. Okay, so eigenvalues, it actually only has 1. We count it twice. So it's 1 with multiplicity 2. Right? So eigenvalue here is just 3. All right. So now I want to find eigenvectors associated to 3. So I want to find eigenvectors associated to lambda equals 3. Now, what I require here is, I could just skip straight to Cayley-Hamilton here, but Cayley-Hamilton kind of, seemed to imply that I needed 2 distinct roots to make this work. So maybe you're confused exactly about how Cayley-Hamilton would work. So it turns out in this case, Cayley-Hamilton, I don't need to do the opposite thing because both of these are roots. So in the Cayley-Hamilton factorization here, this would be, well, in this case, the matrix is B. So this would be like B minus 3i times B minus 3i is the zero vector, is what I get. And so choosing non-zero column of B minus 3i is eigenvector for 3. Right, so because both of them show up here, I can just use the same matrix. So Cayley-Hamilton actually makes this very easy too, but I'm going to do it the normal way, right? So the usual way. Just so you have practice. Okay, so the usual way of doing this is I want to solve, right, a minus 3i times v is equal to 0. So what is, or sorry, not a, b minus 3i is equal to, or times v is equal to 0. So what is b minus 3i? Right, you can do this in your head once you get used to doing matrix algebra like this, but I'm just going to write it out again. So this would be 4 minus 3 is 1, minus 1 minus 0 is minus 1, 1 minus 0 is 1, 2 minus 3, so 2 minus 3 is minus 1. There it is. So that's b minus 3i. Okay, well, b minus 3i times v equals 0. What is that? That is the equation. I'm just going to go ahead and multiply it. So this is v1 minus v2 is equal to 0, and v1 minus v2, sorry, is equal to 0, right? That comes directly from rewriting this thing as 1 minus 1 times v1 v2 is equal to 0, 0. Okay, so this gives me the simple relation v1 is equal to v2. So again, choose, say v2 is equal to 1. This implies v1 is equal to 1. Okay, and so 1, 1 is a vector, right? So then 3, 3, 1, 1 is an eigenpair for B. It's not just an eigenpair, it's actually the only eigenpair, right? That's it. This is it. Okay, because this only has one distinct eigenvalue. Now, let's do Cayley-Hamilton. We can actually do it in this little tiny box here. Cayley-Hamilton tells me that an eigenvector for lambda equals 3 is, because this is a double root here and I only have b minus 3i to choose from, is any non-zero column of b minus 3i. Here's b minus 3i. Well, pick the first one, right? i.e. 1, 1 will work. That's it. So I actually get the exact same one that I got from the usual way. But look how short Cayley-Hamilton is. Look at that. Right? So nice. Of course, you know, you had to compute b minus 3i in either case. So this could be included in this box for Cayley-Hamilton, because just like it's included in this box. So really, the length of method, right, is this box compared to this box. Well, you know, it's not a huge difference, right? So you can definitely use either of these you want. But in this case, we only had a single eigenpair. Okay. So let's see how this all works out here. Now, the next example is the following. So let C be this matrix from before. So here it is. It is 3, 2, minus 2, 3. then we already saw that from previous example, the eigenvalues here are 3 plus or minus 2i. The eigenvalues are 3 plus or minus 2i. Okay, so lambda, we'll say lambda 1 is 3 plus 2i, and lambda 2 is 3 minus 2i. So let's find eigenvectors for lambda 1. So eigenvector for lambda 1, how do I do that? I want to, if I'm using it the usual way, right, so let's solve a minus lambda 1i times v is equal to 0. What is a minus lambda 1i? So a minus lambda 1i is, sorry, I shouldn't say a, I should say c here. My apologies. So there's c. So here's c, it's 3, 2, minus 2, 3. Minus, now is where something interesting happens. This is a complex number now times the identity matrix. Okay. What is the result here? Well, I get 3 minus 3 plus 2i. So 3 minus 3 is 0. This would be minus 2i in this slot. In the next slot, I get 2 minus 0. So that's just, sorry, that's 2. In the next slot, I get minus 2 minus 0. So that's just minus 2. And then in the last slot, I get 3 minus 3 plus 2i. So 3 minus 3 is 0, and I get minus 2i again here. Okay. So how does this work? Well, let's see here. Well, what I can do here is write out this equation just like I would if these were just regular numbers and not complex numbers, right? So if I write this out, what do I get? I have minus 2i, 2, minus 2, minus 2i, times v1, v2. And that is equal to 0, 0. So I get two equations. Minus 2i v1 plus 2 v2 is equal to 0. And minus 2 v1 minus v2, or sorry, minus 2i v2 is equal to 0. Okay. So what do I want to do here? Well, I'm going to pick this one, and I'm going to say this means that minus 2 v1 is equal to 2i v2. If I divide through by minus 2, this means that v1 is equal to minus I times v2. And just as before, what I can do here is choose v2 to be equal to 1. If I choose v2 to be equal to 1, that means that v1 is equal to minus I. And so, this means that minus I, 1, is an eigenvector associated to lambda 1, which is 3 plus 2i. Now, a couple of questions. Now, for the first time, right, all the matrices we've seen so far have just had real entries. But now, we have a vector showing up that actually has imaginary entries. In fact, this will be something that This will be something that always happens when you have a complex eigenvalue. The resulting eigenvector has to have a complex number in it. And I don't mean complex in the sense that, oh yeah, every real number is technically a complex number. I mean something that has non-trivial imaginary part. Okay, so there will be an honest-to-God complex number showing up here. Okay, and it has to work out like that. If you think about it, right, the second you have this equation that CV is equal to lambda 1V, right, because lambda 1 itself is a complex number, to make this make sense at all, V wouldn't be able to be nothing but reals, because then on the left-hand side you'd have nothing but real numbers, but then you'd have a complex number times a real thing. That doesn't make any sense. So it always has to work out like this, right? So it's always going to work out like this. Now I'm going to use Cayley-Hamilton for the other one. Okay, so I'm going to use Cayley-Hamilton for the other one. So Cayley-Hamilton. So for lambda 2 is equal to 3 minus 2i, Cayley-Hamilton says that any non-zero column of c minus lambda 1i, which we have already computed here, right, which is minus 2i2 minus 2 minus 2i. Any non-zero column of this thing is an eigenvector associated to lambda 2, which is 3 minus 2i. Okay, i.e., just pick the first one. Minus 2i minus 2 works. I.e., if that works, what else works? What if I scale this by minus 1/2? Well, this also works, just to make my life simpler. So this means that I1 is an eigenvector associated to lambda 2, which is 3 minus 2i. Now, I want you to ponder hard here. We have found two distinct eigenvectors for these two distinct complex eigenvalues. Do you notice anything about them? You notice anything about these? Recall, right? If lambda is a complex number, we'll call it mu plus I nu. Then the complex conjugate of lambda, written lambda bar, is mu minus I nu. So we have a fact here. If lambda v is an eigenpair for A, then lambda bar v bar is also an eigenpair for A. What this means is the second that we found this, we were done. And we were done by saying, oh, the eigenvector for the other one is just you take this eigenvector and you do the complex conjugate. So everywhere there's a mu plus I nu showing up in the vector, you replace it with mu minus I nu. So the only place is here. So here you have minus I, you replace it with minus minus I. And that's it. So actually, this is kind of counterintuitive, but actually it's the least amount of work to find eigenpairs, for double roots or for complex roots, because for complex roots, even though you have two different roots, you basically only have to do half of this process. You only have to do it for one of them, then you automatically get the second one from complex conjugation. Okay, so that's a nice fact. Now, how does this tie in? So how does this all tie in to solving? This is the big question. X prime is equal to AX. Okay. The answer is, depending on the case, you are very familiar with these cases. So, two real eigenvalues of multiplicity 1, one real double eigenvalue, or two complex eigenvalues. We can write the general solution as x of t is equal to c1 x1 of t plus c2 x2 of t, where x1 of t and x2 of t are determined by the eigenpairs lambda 1 v1 and lambda 2 v2. Okay. So we are now finally at a place where we can write this out. Okay, and this is going to do it finally. Okay, this is going to give us a way of solving these things and of finding matrix exponentials. Okay, so the next lecture we're going to see all of that stuff. Tomorrow's lecture you're going to see all of that stuff, and finally you're going to see how all this stuff ties in together to give you a way of solving this. And then we're going to compare this with the one single solution that we did previously, which was this 3 2 2 3 matrix. We wrote up the solution and I showed you what the matrix exponential would be, what the fundamental matrix would be, all that stuff. So anyway, and so since we're finally finishing this, I'll be able to post another homework for you all, which will probably be the last homework that I post. And then that will be that. So anyway, I will continue on tomorrow, and we're reaching the end. So I will see you all